Okay, this is Paul Gregg, and this is part 7 of my initial trial runs of my physics, math, and engineering STEM course on backyard roller coasters. This last section 7, will be a little scattered, but we'll just put it down and see how it goes. The last thing we want to do before we actually ride people on our roller coaster is some kind of certification testing, which asks the question, how do we test our roller coaster to make sure it is safe for passengers before we let anybody on it? I do have a list of safety rules to follow. Nobody around the roller coaster when it's being run. A fence around it, or at least caution tape around it so nobody wanders in there when it's running. And I always have adult supervision guaranteed by not having a mechanical lift. An adult or a person has to push the cart up the hill, the lift hill. And that guarantees. And you have to have anti-rollback mechanisms on the lift hill in case something happens. You don't want someone running full speed backwards down the lift into some flat, tight turn that would be traumatic. So there's a lot of safety things to think about. We can, if you really want to make sure something's safe, you have all your materials tested for your analysis. There's stress analysis. There's dynamic analysis. We can do element level tests on joints, like the joints and different things. We could test the cart. We could do all kinds of subcomponent tests and things like that. But basically, if we want to run it down the track with sandbags on it or rock bags, and I suggest, as to be really safe, you put 150% or 1.5 times the maximum allowed rider. So whatever the maximum weight of your biggest rider, take 150% of that, 1.5 times that, and run it down the track with that on it. And then we'll say it's certified for that. So I think I have a YouTube video of when I did this for July 15th, 2014. This is the two-dimensional roller coaster BYRC 001, the 84-pound proof test with a 12.5-pound chassis. So what happened there was I put 1.5 times my the weight of my largest. I thought, well, I might run a kid 50 pounds down there, so I took 1.5 times that, 75 pounds, including and then added the cart weight and put that much weight on there. And then I was certain that when I run a child that doesn't weigh that much, I can run it down there and feel very safe. Okay, this is similar to what we do with components on an airplane. I'll just show you that. This is the 777 wing test.
The engineers needed to know if the 777 wings could survive the strongest forces that turbulence or bad handling could produce.
There's a maximum expected operating load on a wing. We put 150% of that on here and see what happens. And this is the 777 test. It actually went to 154% of limit load.
A crowd of observers, including many of the people
which makes
who had
everybody
lived with
really
the plane
happy.
for more than 4 years, fell quiet.
So they're at 150%. They're very excited because now the airplane is certified to fly. This is a fuselage and a wing that are never going to fly in real life. They just make this special airplane just to do this test, and then it's all thrown away. 153 means 153% of design limit load.
154. Whichever way you looked at it, the test was a success.
154. 154. 154.
So that wing is deflecting 24 feet. So when you fly an airplane, you have a pretty good feeling that the wings aren't going to break. Other things. There's a possible, I could keep going on this video for hundreds of hours. I've done lots of this stuff. We could talk about, we talked about when the mass drops out of the kinetic energy equation. Why does a large person slide down a slide faster than a small person? If the mass drops out of the equations. We could talk about that. We could talk about a loop. Bank turns. How do you determine the optimum bank angle going around at a certain radius turn at a certain speed? That's pretty easy to do. We could talk about friction and experiments, how we determine what the static and kinetic coefficients of friction are. We could go more detailed on my spreadsheet analysis. Stress analysis of individual components. Every one of these components in the cart and the track would, if it was a professional job, they would receive a stress analysis in themselves. And if it was more complicated, a complicated joint that we didn't have a characterization for, we would do element level tests. Fatigue analysis, dynamic analysis, testing, all kinds of things we could do. We could simulate things with no limits to, or FVD++, which is computer 3D simulations. We could talk about fracture toughness. My PVC tracks are susceptible to sunlight degradation and less fracture toughness, and I did a lot of testing to characterize that, and decided that we need to paint our PVC so that the sunlight, the ultraviolet radiation in sunlight doesn't degrade the fracture toughness too much. So here's a bunch of extra information. I'm not going to go through this in detail, but here's a discussion about where the sun's energy comes from and where it goes. Calculating optimum bank angles. If we're going around a turn at a certain speed and a certain radius, it's not too hard to calculate the optimum bank angle. And I have a spreadsheet that does that. So when you design a track with turns in it, you can do that. Up until 1980 or so, whenever roller coaster designers did a loop, they always did circular, but that's really tough. You have to, in order to maintain positive G's, in other words, your body being chucked into the force, the centripetal force high enough that you always being pushed into the cart. That's really hard to do with a circle because you have to go really fast, and that makes a lot of stresses. So somewhere in the 80s, someone proposed doing what's called a clockoid loop. It's spelled clothoid, but I think in German it's called clockoid loop. And you have a tighter radius at the top of the loop. And that turns out you can go through this a lot smoother and with less speed. And that's how you see modern roller coasters made, with this non-circular shape. And we can go through the calculations of a loop and why it's kind of difficult to do. You have to be pretty high. You have to have a lot of speed going through it. And I made a spreadsheet that can tell us via these equations we've been talking about how much speed we have to have, how much starting height we have to have, and stuff like that. We can talk about the cart and why I like tubular structure, the efficiency of tubes versus solid, things like that, and go into some engineering about why tubes are more structurally efficient than solid parts, and why I-beams are efficient and stuff like that. We could talk about aerodynamic drag and what the equation is for drag, and how we calculate it. How aerodynamic drag is a function of velocity squared. So another case, if your velocity doubles, then your drag goes up by a lot more than double. And kinetic friction, you can determine there's a static coefficient of friction, a kinetic coefficient of friction, and we can talk about how we determine those. Testing of the cup tie-ins, I identified a weak point as being the joint where these screws go into the PVC pipe holding it onto the 2x4 cross tie. And how do you test that? How do you quantify how much each one can take? Turns out we can do a test. This is in an actual test lab. You just push on it till it starts to fail and break. You track it and you say, okay, where did this break? Something started, the wood started to break and then it finally failed. I also did this when I started out. I made a test track 10 feet long, and I put my first cart on it, and I just loaded that cart with I think nearly 1,000 pounds, and ran it back and forth to make sure that my joints and the cart would withstand it. So each one of these containers is full of water, and what it says here, I think it was 830 pounds. And then I checked the deflections as it went back and forth. But I knew that, this represents, I think, 3 Gs. So in other words, I'm doing a static test of a dynamic situation. So in other words, if I had a 100-pound weight of person and cart and I was doing 3 Gs, that would be like putting 300 pounds on here. And so this is kind of a severe test. It's not really a roller coaster, but it's testing the joints and the cart, testing a lot of things here to make certain that we are going to be safe and these joints aren't going to come apart. This was after that test. I did get a bolt that bent, but it wasn't a grade 8 bolt, so I put grade 8 bolts in and they didn't bend like this. So there's a good reason for spending extra money on good bolts. And that's the conclusion of that test. So there's a lot of things we could continue to do, but basically that's the baseline. In a real class situation, we'd have lots of questions and answers, and I probably didn't cover everything. I probably forgot some things, but I thought it was a good idea to get this all documented. So thanks for listening. I'll see you later.